All right, let's dive right in. Today we're going to explore something that's really at the heart of all modern computing. Drawing on research material from Dr. Sudheendra S G, we're going to talk about the journey from the raw ones and zeros a computer understands to the languages that you and I can actually read and write. Now, especially for you educators out there, understanding this journey, it's absolutely key to demystifying how these incredible machines actually work. So let's get into it. So to get our heads in the right space, let's just try a little thought experiment. Imagine your only way to communicate is with beeps. No words, no writing, just beeps. How on earth would you explain something as basic as adding two numbers? You'd have to invent a whole system, right? A code where, I don't know, one pattern of beeps means take the first number and another means add. Well, this is the exact problem that early computer pioneers were up against, just with pulses of electricity instead of beeps. So how did we get from that really primitive state to where we are today? Well, we climbed what's called the ladder of abstraction, and that's going to be our roadmap for this explainer. We're going to climb that ladder together, rung by rung, starting at the very bottom with the machine's native tongue and making our way up until we get to the languages that look a whole lot more like something a person would actually write. Okay, so our journey starts at the very bottom, on the ground floor, with machine code. You have to forget everything you know about words or concepts. This is the only language a computer's processor, its brain, actually gets. We're talking about a world of pure electricity, signals that are either on or off, which we represent with those famous ones and zeros. Now, you might look at a string of numbers like that and think it's just random noise, but it's not. It has a hidden structure. See, every machine instruction is usually broken into two main parts. The first part, the opcode, that stands for operation code, it tells the CPU what to do, things like add or load or store. And the second part, the operand, tells it what to do it to, like a piece of data or a specific spot in memory. So in this example, 0010 could mean load and 1110 could mean from address 14. The best way to think about it is like this. Machine code is just another way to encode human ideas, kind of like how Morse code is for English. You can say the word hello, or you can tap out the dots and dashes. It's the same exact message, just in a different format. And that's what early programmers did. They'd first plan out their programs in a kind of plain English they called pseudo-code to figure out the logic before starting the painful job of translating it. And that was the massive problem. I mean, can you imagine having to translate your entire program into ones and zeros by hand? It was unbelievably slow, and it was so easy to make a mistake. You flip one single bit, one tiny error, and the whole program could just crash for reasons that were almost impossible to track down. It was clear this couldn't last. There had to be a better way. And that better way was the first big step up our ladder, assembly language. It was invented for one simple reason, to save human beings from the absolute nightmare of writing raw, unreadable binary. It was, at last, a human-friendly way to write machine code. And just look at the difference it made. Instead of that cryptic string of ones and zeros, a programmer could now write something like load_A14. These short, memorable words are called mnemonics. Now, it's still a direct one-to-one translation. One line of assembly equals exactly one machine instruction. But for a person, it is infinitely easier to read. A special program called an assembler did the boring work of turning these mnemonics back into the binary the computer needed. But, solving one problem often creates a new one. Assembly still had a really big weakness. You see, programs are constantly needing to jump from one section of code to another to do things like loops or make decisions. And in early assembly, programmers had to tell the computer to jump to a specific hard-coded memory address. And this is where everything got super fragile. Imagine you have a command that says, jump to line 41. But then you realize you need to add one new instruction way back at the beginning of your program. All of a sudden, everything shifts down by one. The code that was at line 41 is now at line 42. So you'd have to go through your entire program and manually find and update every single address. It was a total maintenance nightmare. The solution was simple, but honestly, it was genius. Labels. Instead of telling the computer to jump to a specific number, programmers could just say, jump to loop_start. They could give meaningful names to parts of their code and let the assembler program figure out the correct memory addresses automatically. This was a huge quality of life improvement that made code so much more robust and easier to work with. So things were getting better. But even with these improvements, assembly was still really low level.
Programmers had to think like the machine, you know? They were managing every tiny little step, juggling data and things called registers, and keeping track of memory. Writing anything complicated meant writing hundreds or even thousands of tiny instructions. The next step on the ladder, it wasn't going to be a small one. It was going to be a revolutionary leap.
And the visionary behind that leap was the incredible Grace Hopper. She came up with this radical idea. What if a computer program could do the translation for us? Not just a simple one-to-one translation like an assembler, but a program that could take a single, powerful human-like instruction and translate it into dozens of the necessary low-level machine code instructions. This program, she said, would be called a compiler. And here's the beautiful simplicity of her idea. A human programmer could now write something that looks like simple algebra, C equals A plus B. And the compiler would do all the hard work behind the scenes. It would generate all the machine code to load A into a register, then load B into another register, add them together, and then store the result back into C. The programmer didn't have to think about any of those hardware details anymore. Once the compiler was invented, it was like the floodgates opened. For the very first time, programmers could create languages that weren't tied to a specific computer's architecture. Instead, they could design languages to solve specific kinds of human problems. And two giants emerged in the late 1950s. First up was FORTRAN, which is short for Formula Translation. And just like the name says, it was built for scientists and engineers who needed to do really complex mathematical calculations as fast as possible. Then came COBOL, the Common Business-Oriented Language, which was designed for data processing, the kind of stuff that businesses needed to do. But COBOL's biggest innovation, the real game changer, was its focus on portability. Before COBOL, a program written for, say, an IBM machine was totally useless on a competitor's machine, like a UNIVAC. COBOL introduced this idea that you could write your program one time in this common language, and as long as each different computer had its own COBOL compiler, that same program could run anywhere. For businesses, this was a massive, massive breakthrough. So we've climbed the ladder. We went from raw binary all the way to these powerful, high-level languages. Let's just take a moment to look down from the top and really talk about why this journey, this abstraction, actually matters so much, especially when we think about the world of education and beyond. Because at the end of the day, climbing the ladder of abstraction wasn't just about making programming easier. It was about changing who could program. It democratized computing. Before, you basically had to be a hardware specialist. Afterwards, you just had to be an expert in your own field. A scientist, a doctor, an engineer, or yes, even a teacher who just happened to have a problem that needed solving. High-level languages gave them the tools to solve it themselves. And the progress was just breathtakingly fast. I mean, in just over a decade, we went from people literally flipping switches to assembly to Grace Hopper's first compiler in 1952, and then to world-changing languages like FORTRAN and COBOL. Every single step was about hiding the complexity to empower more people. This whole journey, from the very beginning, has been about one thing, getting closer and closer to a point where we can just tell a machine what we want in a natural way, and it just gets it. Grace Hopper started us down that path. Today, we see it continuing with things like AI-assisted coding tools. So the final question to leave you with is this. What does the next rung on this ladder of abstraction actually look like? What's the next great leap that will make computers understand us even better?